Welcome to a quick lesson on solving force problems in systems of objects. This is a nice little setup that can save us a lot of trouble and time if we use some things that we know about a system and apply rules. So in other words, we can kind of cheat from what we've been doing before. So you know enough about free body diagrams and writing net force equations that now we're comfortable showing you how to cheat a little bit to save some time by doing zooming out for system analysis. This is a sample problem from About Problem Solving Part 4. And so that's near the back of the workbook. If you have not read the lesson for that, About Problem Solving Part 4, I'm going to urge you to go do that before you watch the rest of this video. This is a sample problem from that page. Okay, so let's go ahead and get a look at this. We have object A is 2 kilograms, object B is 1 kilogram. We have no friction in this system. And from our experience, we can say, hey, I'm pretty sure that B, because B is pulling down here, that's going to pull A forward. And for every centimeter that A moves forward, B is going to move down. So we're using our experience of systems like this to look at this and go, this could really just be one object. And so if I draw a free body diagram for the system as a single object, instead of just drawing a box for this free body diagram, I am going to roughly sketch what our system looks like, and I'm going to put this boundary around it. And this there's something mentally that helps us do a better job when we actually have the system and we're picturing that this one object can move down and this one object can move right. And it helps us look for the forces from outside, because when I do this free body diagram, I'm only going to include forces from outside the system. So what are all of the outside forces? Well, we have force of gravity pulling down on B. We also, because Earth is outside the system, Earth pulls down on B. Earth also pulls down on object A, but that's not really going to cause the system to accelerate, because A is not going to accelerate down into the table. And in fact, the table, our surface, is pushing up and canceling out. So we have normal force from the table, and we have force of gravity A, and it says which of these forces is actually affecting the acceleration. Really, this is the only guy causing any acceleration. These two are canceling each other. Okay, it says, what about tension? And because you might be saying, well, gravity pulls down, but tension pulls up, and that's an opposing force. And if we were doing the free body diagram for just object B, yeah, tension is from outside. The rope is an outside force. But in this diagram, the rope is inside the system. So that's not an outside force. This would be like worrying about the forces between your ligament and your kneecap. We do a lot of things where, this is connected to that, that we don't worry about on an everyday scale. We can choose to zoom in, or we can choose to zoom out. So here we've zoomed out and we're looking at this system as a whole. Okay, so when I did this, I could write a net force equation. And in this net force equation, instead of just saying right, left, up, down, basically we have specific rules for this system they're kind of unique. If object A moves right, object B moves down. And if object B moves up, then object A could move left. So really we have these kind of two directions to it. And our force, our accelerating force for object B, is pulling the system down and to the right. And so the whole system wants to go in that direction. The accelerating force is causing that. Do we have anything resisting this? No. We have no resisting force, nothing opposing. So accelerating force minus any opposing force or forces equals MA. Now, always pay close attention and label your masses very carefully in this. This is the mass not for object A, not for object B. but for the system. So, sorry, I have a kitten who's getting involved here. All right, got it set up. So this is the mass for the whole system. So accelerating force minus no opposing forces is the mass of the system times A. And this makes it pretty easy to solve for that acceleration. It's the one accelerating force divided by all of the mass that's being accelerated. So we have mass of object B times G, force of gravity for B, versus mass B plus mass A. And so that's going to end up being about 10 newtons is the force for gravity B, divided by 1 kilogram plus 2 kilograms, or 3 kilograms, to get 3.33 meters per second squared. And our kitten is invading again. Okay, so we have been able to solve for the acceleration. This acceleration is true throughout the system. It was for object B and object A. And in fact, this is why we could do, the fact that we knew for object B and object A that they had to have exactly the same acceleration, this is why we could just treat them as one single object. Their motions were linked together. Now, what do we do if we want to find the tension? And in fact, on the about solving problem solving page, the next question asks, okay, can you find the tension? And so this system was really good at coming up with the acceleration, not so good for finding stuff inside the system. But this acceleration could be useful because now I could, for example, just do the free body diagram for object, we can choose either one. Let's choose object B. And I could have force of gravity B down, force of tension up. I know that this object is accelerating downward, so I'm going to take force of gravity B minus force of tension equals MA. Which M am I talking about? Well, this equation goes for this diagram, and the only mass here is mass B. So force of gravity B minus force of tension equals MBA. If I want to solve for the tension, I'll push that force of tension to the other side. We'll add force of tension to the right. We'll subtract MA. We get force of gravity B minus MA. And that leads us to force of gravity B for our 1 kilogram hanging object is about 10 newtons minus 1 times 3.33. And that's going to get us pretty close to 6.67 newtons of force. So our force of tension, 6.67. And so we could have done individual free body diagrams and set up a system of equations and solved for the tension and the acceleration. But this could be much, much easier. If you have a system, go ahead and find the acceleration right away because it's pretty much always useful. Sometimes that's all you even need to solve for, and that's it. You'll be done with the problem. If you need to go deeper into the problem, you can do a free body diagram for one of the individual parts of that system, write the equation, and now that we have the acceleration, that equation will often be pretty easy to turn around something useful. So the last thing that I want to mention about this is you can draw boundaries anywhere in between. You can do it for the whole system. You can do it for a part of the system. If there's 3, 4, 5 objects, you could include only 3 of those. So you get to draw boundaries. And if you get clever about doing this, you can really, really speed up your problem-solving process. So this is the last major piece that we were working on for topic 4. Take some practice, take some time to do it, because we can take some very complex situations and analyze them very quickly now that we know how to deal with free body diagrams and we know how to cheat a little bit. All right, talk to you later. Bye. And here's the kitten who couldn't stand to be ignored.